Thank you very much. So let me share my presentation. Can everybody see this? Good.
Yes, it's great.
So yes, so I'm from the Deep Learning Lab at Tel Aviv University, and we've been doing a lot of explainability in neural networks. And I want to share why I think this is important and where is it going, and how to apply it to the very latest models, and also how to make innovative use of it in order to meet the real world demands from AI systems. But before going forward, let me talk a little bit about what we do at the lab as a way of introducing myself. So we are trying to be as diverse as possible. And if you're interested in anything that has to do with deep learning, we would be very happy to discuss how it would apply to what you're trying to do. And we are trying to always keep an open mind to new applications. So just to show some of the diverse projects that we've been doing a lot of video analysis and image analysis. This is the bread and butter of the lab. So in this case, this is one example work that you see. It's the state-of-the-art work in real-time semantic segmentation. So the input is an image. The output is the semantic segmentation of the objects in the image. So the cat and all the objects in the background and so on. And the challenge is how to do it not only accurately, but also in real time. And this is what we do in this work, which was published in ICCV. And this is another work that was published at ICML, in which we do something completely different. We are given the specifications of an antenna with regards to the layout of the mobile phone and the frequencies that we need to work in. And we are designing an antenna. So this is a work that was also recently published. Completely different domain. We have been working on quantum computing, trying to figure out what's the best way to compile programs in order to make the execution with the D-Wave hardware as efficient as possible, also with the deep learning tools. The work is also, the lab is also part of the Cybersecurity Center at Tel Aviv University. And I would like to invite you to look at the activities of this center. For example, there's an annual AI conference. This is very interesting. In this case, what we try to do is to demonstrate that using neural networks, we can perform what is called a cold boot attack. Somebody turns off the device, but the memory is still alive. Can you recover the secret keys this way and suggest new keys that are more resilient to this effect? So this is using another form of deep learning, using what is called neural belief propagation in order to solve this problem. In yet another project, we're working a lot on medicine, and in this case on detection of COVID in CT, obtaining state-of-the-art results. And also we are interested in fields such as neuroscience, trying to understand the personal traits of a person from the fMRI scan, trying to recognize the disease states and try to tailor the treatment for the specific patient. So this is basically just sample projects to show that we are very diverse in what we are trying to do. But what I really want to talk about today is explainable AI. And I'm going to use some slides. Let me give some slide credit from a company called Comprendo AI, which licensed some technology that I will talk about later on from Tel Aviv University. Tel Aviv University is very open to licensing agreements. So if you have any need, I'm sure that the university would be very happy to help you with addressing those needs. In any case, Comprendo AI took some of our explainability patents, licensed them, and I will talk later on about what they're actually doing. But for now, let's think about explainable AI in very general terms. So as you know, AI models are everywhere these days in very mission critical systems such as autonomous cars, medical treatments that we discussed before. Criminal justice systems might use them in order to standardize the way that rulings are made. Of course, in finance and insurance, they are becoming more and more critical, and this affects the lives of everyone. And also in other places such as social media and e-commerce. So with this great power, as they say, comes great responsibility. But AI systems are not up to the task because mostly AI systems are what is called black boxes. You give the input, you get the output. You don't know what happens in between. You might know the architecture of the neural network, but it doesn't tell you a lot about the reasoning process. And if you go to a human expert, they make a decision, you ask them, okay, I understand the decision, but why did you arrive at this specific decision? With neural networks, we don't have this capability, and this is what we are working on with Explainable AI. And this is critical because, for example, in some places, an AI system decides whether the CV of someone is going to pass to a recruiter or whether it's not going to pass. So it's actually, it's affecting human lives, whether they are being recruited or not. And in this case, Amazon built an AI system for recruiting, and it was biased against women, which caused a huge problem for Amazon. And the system was basically discontinued due to this issue and other similar issues. So the issue of fairness is very important. In another system, this is a European company that had an algorithm that assigns work to the delivery person. And it turned out that this wasn't as transparent as needed by the regulations. And it also was a bit biased against some of the writers. And some of these biases are illegal. So in this case, the system cannot be used, and the company is getting fined for such violations. In another very famous example, Apple wanted to start to give credit cards in collaboration, I think, with MasterCard, and they had the black box system for assigning credit score. And it turns out that exactly the same data, but changing the gender of the person, the system made different decisions, which is of course very biasing, and the system had to be discontinued. And this continues on, and in healthcare, this is very important, whether you approve somebody's claim, what kind of treatment are you going to approve. This is all very crucial. And you must make sure that the system is not biased against specific ethnic groups. This is, of course, raises a few questions. For example, if the health situation is different between different ethnicities or different genders, whether this is a biasing result or whether this is something that you need to take into account. So all of these are very important considerations when we discuss fairness. So I would like to argue that the key to fairness and understanding, and this is another system story about college admission that turned out to be biased against lower class people, which raised a lot of protests. So I would like to argue that the key, and we will see later on examples, for having a fair system is making it transparent. We would like to have a system, an AI system, that we understand the reasoning behind what is going on, and then we can address it. So if we understand the system, we can build user trust because the user can see, we can expose the reasoning, the user can understand what is going on and why it's going on, and then benefit from this. We can prevent bias because we can see whether the decision is being made based on variables that are protected from the fairness perspective, such as age, gender, ethnicity, and so on. And we can also give some feedback about the performance of the AI, whether it makes sense. Either the users can give the feedback, or the people developing the system can look at the performance and understand the reasoning and then fix the system. Also, from the external point of view, we would like to have the AI system compliant with the various regulations, which can only be if we open the underlying reasoning. And from the internal point of view, we would like the reasoning to help us understand the data that is flowing, the problem with the data, some challenges, some opportunities that we are missing, and so on. So let me start with talking about explainability in the very specific context of transformers. And I don't know whether you got exposed to transformers in the conference so far and how much exposure did you see, but basically transformers are the most powerful model that is being used now in fields such as natural language understanding and also computer vision. So if you think about the earlier days, people used the CNNs, maybe RNNs, maybe move to ResNet type of architectures. Currently, all the recent results are almost entirely, if you go to the conferences, based on transformers. And transformers are regarded, of course, as a black box, but they also have some challenges with regards to the explainability. The methods that were developed for explaining CNNs, convolutional neural networks, don't work for transformers. So we've been doing some work, especially on this point, how to open up the transformer, how to emphasize what is going on inside the transformer, and I will show some examples of what we did. So what is transformer? A transformer is an attention model. Basically, you have the input data, and then the input data is getting translated to a higher level of representation. And every part of the data communicates with the other parts. This is called attention. And there's a very specific multi-head attention mechanism that is being used in transformers that turns out to be very powerful. And already when it was demonstrated, when it was presented for the first time, it was already demonstrated that it's state of the art, for example, in machine translation, which is a very well-studied task in natural language understanding. So this is a view of the attention mechanism. So imagine that there is an input that is a sentence. This is a natural language understanding scenario. So every word is a token in this case. And this is the next layer. And every element here is associated with the underlying token. So this is the cat token, even in the next layer. But it's connected to all the other tokens in the previous layer. And the strength of this connection is what is called an attention. And when you gather all the information, this is called pooling, and it's done through the attention mechanism. So this type of communication gets you the information from one layer to the next, and it repeats with an attention mechanism this way from one layer to the next. And then the same idea of transformer was taken in order to perform what is called self-supervised learning. Self-supervised learning is when you take a corpus, in this case, a huge amount of text, and you train the system without supervision to obtain a very powerful representation. So the way that this is done in the BERT system is that you take the transformer model and you use it to predict a word that you must count. So you have the entire sentence, you take one word and you hide it. And the task is to predict this word. So you don't need an outside supervision, it's just a word from the sentence. The network does not see this word, and then it tries to guess this word. So this is a very simple task. Why do we use it? We use it in order to get the neural network, in this case the transformer, an opportunity to learn a powerful representation. Because in order to understand the missing word, you need to understand the context of the text. So this is done with transformers in the BERT system. And what is amazing is that you take the BERT system after it is trained and you fine tune it. You adapt it a little bit to a new task with relatively few data points, few data samples, and you get state-of-the-art results across multiple NLP tasks. So tasks such as understanding the part of the sentence, answering questions, and so on. And then after the huge success that transformers had in language understanding, it came into computer vision. The way that this is done, you get an image, you need to transform it into tokens. Such as in text, you have the words, these are the tokens. In an image, what is being done, you take the image and you break it down to patches. And each patch becomes a token in the image. So you transform the patches to a list of tokens, then you apply the transformer, and then you get a classifier. This is called vision transformer or visual transformers, and it's currently leading in multiple computer vision benchmarks. It's a very powerful technology. So if you go to the recent computer vision conferences, there's a huge shift from convolutional neural networks to transformers. And people have been doing amazing stuff with transformers. For example, what is called the DALI system by OpenAI is you give an input that is a sentence. In this case, you describe an image, an emoji of a baby penguin wearing a blue hat and so on. And the system generates an image of this penguin. But it never saw any penguin like this in the training set. This is basically a de novo generation of something that was not seen before and matches the description. This is pretty amazing and an amazing work by OpenAI from the last year. So we have these transformers and they're becoming increasingly important, but we need to add explainability. For example, if you think about one of the most powerful language models called GPT-3, it was shown to be racist and also to be gender biased. What does it mean for a language model to be racist? If you, for example, start a sentence and you say, the Muslim went, the rest of the sentence is maybe going to be associated with negative things. And if you go to and say a Christian went, it wouldn't. So the Christian went to church, and the Muslim went, and then it would be something negative, participate in some terror activity or whatever. So this is a type of racism that exists in such models. It's not on purpose. This is the training set that they were exposed to. Basically, the word Muslim appeared in a negative context, and this is how they learned to make this association. So we'd like to understand the inner working and then be able to fix what is going on. And in this case, as we said before, users would have trust, we can fix biases, and we can also understand the model better and therefore improve it. So if you think about a transformer, so these are the tokens, and these are also the tokens, and there's the attention. Basically, the color encodes the strength of the attention between them. And the CLS is a special token that is used to make the decision. Let's say that we want to classify whether a certain text is positive or negative, as a positive or negative sentiment. So we add a token where we would get the classification from. This is a technical point. And this token basically has attention to each one of the other tokens, which are words. So one can think that maybe these attentions explain which word is more important and which are not, but it turned out that this is not enough. The attention that you get from the token to all other tokens is just one point in the network. There are multiple layers, multiple attention maps, multiple attention heads, so this is not enough. So what people did is come up with a solution to aggregate across attention layers and aggregates across attention heads. And one such system is by Abner et al., which published it in ACL 2020. They suggested two solutions. One of them is inefficient, using what is called rollout, that is matrix multiplication and averaging over the heads. And another one that is called max flow, which is slightly more accurate, but is not as fast, and using the max flow algorithm. As we show, both of these solutions are not ideal. They ignore parts of the network that do not have to do with attention, such as the relevancy map that you get from the gradients. They are not being taken into account. The attention is just one part of the transformer. Also, the way that aggregation is performed is not ideal. So we came up with the solution that takes the transformer blocks, separates it into multiple parts, takes into account the skip connections, all the elements with regards to gradients and relevancy and attention together. And we come up with a solution that is much more accurate. So this is an image of a dog and a cat. If you ask a rollout, why is this a dog? You would get this attention. This is what you get by our method, which is much more focused on the actual dog. If you ask the explainability method, why is this an image of a cat? There is a cat over here. You would get in other methods exactly the same solution. So it doesn't take into account the classification. In our method, it takes into account the classification. You get the cat, and it's very much focused on the cat itself. Similarly with the zebra versus the elephant, while other methods that were suggested in the past cannot necessarily make this distinction. And since it's transformer, it's not only for images, it's also for text. So if you give it a review and you want to ask, okay, why is this a negative review? Why is this a positive review? You want different words to be highlighted. For example, in this case, negative because it's joyless. And it's positive because there's enthusiasm. So there are different words that point to different decisions, and the systems allow us to see which contributed to each one of the conclusions. Our work was then later on cited by different people who used it in order to understand where one can find the actual infection in lung images, the explanation of specific facial expression, and the identification of anti-spoofing when somebody comes to a face recognition system wearing makeup or some sort of a mask. So these are the pixels of the image regions that led to this decision. So far what we discussed is actually just one type of transformers. It's this one that is used for classification. But transformers are also used to link images and text, as you saw before, let's say with the DALI example, and also for generating new content with an encoder-decoder type of network. So we made an extension of this work that allows us, for example, this is from a system that links a sentence in English to an image. And you can see that we can identify the correct location of each one of the elements. So if the sentence says there's an elephant and a zebra in front of a lake, the system can point to every text token where it is in the image. And also for networks that are being used for object detection, you can actually see the segmentation that led to the specific detection. Also for visual question answering, there is an AI system that gets an image and a question and returns an answer. We can see what was important in the question and what was important in order to generate the answer. So I have a few more slides to share, but maybe there are questions instead of the slides for the remaining of the session. Is there any question that you would like to bring up?
Well, actually, I'm very delighted to listen to you, Lior. So please go on. I guess the audience will like this better.
Okay. So let me use the few remaining minutes to discuss the system that was licensed to Comprendo AI and the reasoning behind it, which is even more important. So usually when we talk about explainability, one builds the model and then they try to explain what is going on. But this is something that is really problematic for two different reasons. One of them, once the system is complex enough, you cannot explain it. So every explanation, I would say, is some sort of a superstition that you give somebody some notion of what is going on, but it's not an actual explanation. And also, if you build it in a way that is not explainable, then the reason is too complex to understand anyhow. So instead, what we try to do now, in multiple work, this is one of them that's very powerful. We take a neural network in order to build a decision tree. A decision tree is very easy to explain because if you have a credit score above 50, go right. If you have a mortgage, go left, and so on. This is an example from a financial system. Everybody can understand the decision tree. If we can build a decision tree that is as powerful as a neural network, then we have something that is explainable by design and also very accurate. And this is what we are doing in this specific technology that we published and then was licensed. Basically generating trees that anyone can understand, but are as accurate as neural networks. So if this is an example from a credit assignment task, and this is another similar assignment, and so on. And the nice thing is that this can readily be used to prevent bias, because if, for example, we want to ask whether the system is biased against women. So one solution is not to check whether the client is a woman or not, but this is not enough. Because if we ask whether somebody does martial arts, then most of the people who do martial arts are men. So this is already biasing. So we can identify such cases and then augment it by adding a specialized tree that corrects this specific bias. So to summarize, we talked about many phases of explainability and how it can be used. We talked about heat maps in vision, in text, and then we talked about other work for generating explainable models using the neural network. And we're using explainability today everywhere. So we are using it, for example, in genetics in order to find the causal gene for a specific type of cancer diagnosis. And we're using it for scientific discovery in order to find out the underlying factors for a decision, and so on. If you have any question about explainability or anything else, please reach out, write me, very easy to find in Google, and I will be very happy to answer. Thank you very much.